welcome to Extra Credit Part 3 of 3. Today we are talking integrals, but not just any old integral. We are getting indefinite. We are going to infinity, and we are tackling the antiderivative, aka the indefinite integral. Which leads me to my first point. Hope you have your paper handy. Don't let vocabulary intimidate you. The antiderivative is the indefinite integral, which is the antiderivative. As far as we're concerned, they are the same thing. So what is an indefinite integral exactly? Well, mathematically, it's how you undo the derivative. And for those of you that took a legitimate Calculus 1 course, you'll know that the derivative is a tangent line or slope of a given point along a function curve. So in terms of graphs, an integral is how we get the area underneath that same curve. Here's a visual example of what I mean. When we take the areas, we're essentially just adding up small chunks, a technical term, of space under the f of x line, or the function line. The smaller the columns become, the more exact our area calculations will become. So if we keep making those columns smaller and smaller, we can add up infinitely many chunks of area and get an almost exact value, which, surprise, is what it means to take the indefinite integral. So now you're probably wondering how we do this. Well, it's pretty simple once you get the hang of it, and here are some guidelines that'll help you get started. What you'll need to do first is find a comfortable place to sit, focus your calculus intentions, and repeat this mantra. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Add 1 to the power. And after that's become constant background chatter in your brain, don't forget to tell yourself to not forget the constant. Always, 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 when dealing with indefinite integrals, add a c to the end. Now that you've mastered those, you can utilize these fancy integral rules. With integrals, we're allowed to move things around and create problems that are easier to solve. These two basic rules are examples of that. Pause here and take a photo if you'd like. In the first one, we have a cleverly labeled constant c in front of our function f of x. In indefinite integrals, we're allowed to bring the constants out front as long as they're being multiplied against a function. Below that is another handy rule that tells us that if we have a nasty-looking integral where we're supposed to add two functions together inside, we can break them apart and integrate each one separately, allowing for less heartache and headache in the process. Here is a short list of a few more indefinite integrals that you'll come across. We'll have a couple of these in our upcoming examples, but take a picture, and if I were you, I would just memorize these now so you don't have to think about them as hard later on. Also, if you're using this calculus book, there are some integral tables at the back of the book and a really handy integral table on 495. You should probably get familiar with that. Back to the task at hand. Here are the 3 examples I'm covering, so let's get into it. For numbers 1 and 2, we're going to be first taking the derivative, and then from there, we'll take the integral just to really illustrate what's going on here. Number 1 gives us a function 6x squared minus 6x plus 1. This is a standard algebraic function that would give us some kind of parabola that translates to the right and down a little bit from the origin, which is all fine and dandy, but let's take the derivative so we can really figure out what the function of the slope is at any given point. So we'll bring the power down to multiply by and then subtract by 1 from the remaining power. So 6x squared becomes 12x to the 1, and 6x becomes 6 times x to the 0, which is 1. So we'll just write a plain 6. Okay, so after all that, we'll integrate to undo this. We're going to take our derivative, draw an integral sign out in front, and integrate with respect to x. That's the dx. Here we'll simplify and separate into 2 integrals. This gives us the integral of 12x dx minus the integral of 6 dx. So back to our mantra, we're going to add 1 to the power and divide by the new power. We'll get 12x squared divided by 2 minus 6x. And don't forget that mystery constant. Mine kind of looks like a cartoon squid, but you get the point. So our answer is back to the original, but we must remember to include the constant that the derivative got rid of in the first place. In number 2, we get a little bit crazy with the exponents. We have 4x equal to x to the negative 3/4. When we bring that power down to multiply and subtract 1 from the power, we get negative 3x to the awkward mixed number negative 7/4, all divided by 4. Not lingering too long on that, we'll take that, bring it over, integrate our derivative. I know you're super sharp and realized before I did that I forgot to write dx. Good job. Don't be like me. So once you add 1 to the negative 7/4 exponent and divide by the new power, your 4's in the denominator cancel, leaving 3 on the bottom to cancel with the numerator. Cool. After that, we simplify a bit, and we are back to x to the negative 3/4 plus a constant. Last but not least, we are at number 3. We are given an indefinite integral to solve that's already in indefinite integral form. First, you'll notice that we have another ugly exponent situation, but because we're at the end of Calc 2 and we know how to use sub, let's do it. Off to the side, we're going to make x squared our u, and the derivative of u will be 2x dx. Let's take that u and plug it back into our equation. Awesome. Next, you'll notice that our du doesn't exist anywhere, and that we still have a dx in the integral, but don't worry, we can add some constants in this to make it look however we want, but remember, we need to balance inside and outside of the integral. So, if we need a 2 inside, we'll have to add a 1/2 outside the integral in order to balance it out. So we shuffle around our numbers a bit, and we see that after we added some constants, we are able to fully substitute to u. And as you may remember from the short table earlier, e to the u will just integrate to e to the u, and du goes away, leaving us with 1/2 e to the u plus c. But our original problem was in terms of x, so we need to make sure that the u's are taken out. So our answer is 1/2 e to the x squared plus our friendly constant c.